how do you get the average distance from the mean? Well, we know how to calculate an average, right? So to get the average distance from the mean, your first instinct would be just to calculate an average of those distances, right? So again, in mathematical symbols, what you would do is you would add up all of those distances. So each observation in your data set has a distance from the mean. You could add all of those up and then divide by n to get the average, right? That's a good first instinct. Of course, there's a problem with that. There's going to be a problem with that quantity, right? So what's the problem with that? Well, the problem with that is it's going to fail because remember that some of the distances are going to be negative and some of the distances are going to be positive. Some people do more homework, some people do less homework. In fact, if you add up all of those negatives and positives, you're going to get exactly 0. So when you try to calculate the standard deviation in this way, it actually completely fails because you end up with a value of 0, and that's because you've got negatives as well as positives. So the problem is the negatives. So the next thing you might think is, well, how am I going to get rid of the negatives? What do we do in math if we don't want to deal with negatives? So how can I get rid of negatives? Your first instinct on this might be to turn to absolute values, right? If you take the absolute value, you could do the absolute values of the distances, and that would get rid of the negatives. It's not going to add up to 0 anymore. However, it turns out that it's very messy mathematically to deal with absolute values, right? If you remember back to like Algebra 2 in high school, when you dealt with absolute values, funny things happened, like less than signs got flipped around to greater than signs and all these kinds of funny things. So, mathematically, we don't want to deal with absolute values. So what's another way to get rid of negatives? So another way to get rid of negatives is to square things. So that's actually what we're going to do. This is how we're going to calculate standard deviation. We're going to square all of the distances from the mean in order to eliminate the negatives. So rather than take the raw distances from the mean and add them up, we're going to square those distances first and add up the squared distances from the mean and get the average squared distance from the mean. This is something that we call a variance, and in terms of symbols, I represent this as an s squared. S will be the standard deviation, so s squared is what we call the variance. So s squared, the variance, is the average squared distance from the mean. And I'll just write it out one more time here. Formally, I just want to point out that the official formula for variance, which I've now got up, we've gotten to the official formula here for variance. Again, s squared is the symbols I use to represent a sample variance. Notice that the formula looks just slightly different because in the denominator, I'm not dividing by n to calculate the average, which is the way we usually calculate average. I'm dividing by n minus 1. This is a little technical point, but I just want you to understand why it's there. So it turns out that the reason we're dividing by n minus 1 here is that we've lost what's called a degree of freedom. So when we calculate variance or standard deviation, we have to calculate something else first. We have to calculate the mean first. By calculating that mean, we lose what's called a degree of freedom, and we're therefore only have n minus 1 degrees of freedom. So that's why we're dividing by n minus 1 rather than 1. For all practical purposes, it doesn't usually make a huge difference, right, whether you divide by n or n minus 1, because as long as n is pretty big, whether you divide by 99 or divide by 100, it's not going to make a huge difference. But that's why technically that's in the denominator. So what's a degree of freedom? Well, a degree of freedom is let's say I've got a data set of 100 people, and I were to calculate the mean for that 100 people, let's say the mean age, and I were to give you the mean, and I were to give you 99, the ages for 99 of the other people in the data set. If you had 99 of the ages and the mean age, you would be able to calculate back for me exactly that 100th person. So that means that once you've calculated the mean, you only have 99 degrees of freedom left because that last person, that 100th person, is fixed. They can't be anything else. Once you have 99 in the mean, there's nothing else that person can be. So you've lost what we call a degree of freedom. Again, that's a technical thing, but it will come up again. So I just want to point out that that's there. Of course, we start by calculating the variance, the average squared distance from the mean, but that would, if you're not going to report the variance in your paper, because that would mean you'd be reporting things in like age squared, years squared, homework squared, hours squared, and so of course we're going to want to get back to the units of the original data. So we're going to square root it, And that's what the standard deviation is. It's the square root of the variance. So we start with the variance and then we square root it to get the standard deviation, to get back to the original units. And I use as a symbol for that, I use s. So s squared is the variance, s is the sample standard deviation. So that's just to take a square root to get back to the original units. That's what your standard deviation is. Now, I just want to point out that there are consequences to the fact that we did this little squaring routine. So the standard deviation at the end of the day is not exactly the average distance from the mean. It represents sort of the average spread or average scatter, but it's not exactly the average distance. We have this little squaring trick in there, right? And so one of the consequences of that squaring trick is that things that are farther from the mean are actually going to have more influence, are going to contribute more to the standard deviation than values closer to the mean. So for example, if the mean is 5, then if you're talking about a value of 6, you're only 1 away from the mean. If you square 1, you're still at 1. But if you are 5 away from the mean and you square 5, you're amplifying that distance. So now it's a distance of 25. So we're going to, all the, this says is that when you have values that are extreme, those are going to have a lot of influence on the standard deviation in the same way they influence the mean. Let me just give an example calculation here of how you'd actually go about calculating the standard deviation by hand. So remember, we had this little hypothetical data set which had 8 people with 8 ages in it. They ranged from 17 to 38. We calculated in a previous module that the mean for this data set was 23.25. So again, we have to calculate the mean before we can calculate the standard deviation.